Good morning, everybody. Thank you for joining. To start the morning, we have Prof. Sukyoung Yi, who is professor at Yonsei University, who is going to talk about new galaxy formation simulation. So Sukyoung, I will give you a 3 minutes warning before the end of your talk.
Okay, thank you. Good morning, everyone. Good to see you all, old friends and new friends. And today I'm going to give you a brief progress report on the new galaxy formation simulations we are carrying on at Yonsei. The team will introduce the science projects individually in their own talks. On the top, DJ is no longer with us. He's now in the States. And Jinsu, the speaker of the following talk, will talk about star formation history and velociraptor galaxy identification. And Sanu has given her talk on mass segregation. And San is behind all of my simulations. And Seyoung and Jaekyung will talk about their sciences later on. And Ryan Jackson will join the team next month. And behind everything, there is Tae-san as a mentor. The first, almost everyone seems to be familiar with the New Horizon simulation. It's a zoom-in simulation on a small region of the horizon Asian volume. Nice thing about this new simulation is its high spatial resolution and mass resolution. Spatial resolution is about 8 times better than TNG 50. So it's really nice and reveals the properties of galaxies in greater detail than ever before possible. So these are the mock images made by JK Zhang, my student, with SCUT. So it's a realistic radiative transfer approximation. And as you can see here, galaxies look quite good. Not only on face-on view, but also on edge-on view. You can see the nice dust lane as realistically as possible. And in comparison to the real galaxies, and we are actually getting quite close to reality in terms of the galactic structure, because we have very good spatial resolution, and also the shapes, because we have good mock imaging capability. But New Horizon is not free of problems. It has several problems. To tell you just a few of the famous or maybe infamous problems. One of them is the stellar mass over halo mass ratio. So this is halo mass on the horizontal axis. And in the vertical axis, you have stellar mass over dark matter halo mass. And these lines are the typical empirical relation. And the New Horizon galaxies are the gray dots. So they are just too much in stellar mass. Most of them. The most massive galaxies seem sort of okay, but the intermediate mass galaxies are all overshooting by almost an order of magnitude. So we had to do something to improve on this. Second problem is the black hole mass. So this is black hole mass versus stellar mass. And there are many dots. Don't look at all the dots, just look at the orange dots. The orange dots with black circle, those are the New Horizon galaxies. And compared to the empirical lines, New Horizon galaxies always go under the empirical relation. To make the matters worse, and lots of New Horizon galaxies do not let their black holes grow at all. So they just have the initial mass and then they don't grow. It's because black holes have very much difficulty settling down at the center of the galaxies, as Marta introduced yesterday. This is probably due to the introduction of the high spatial resolution. So New Horizon is unprecedented high resolution. And then when you resolve the central region, the gas motion is resolved, the stellar motion is resolved, and then you can resolve very fast gas streams And even if there is a lot of gas in the galactic center, if galaxy motion is resolved to be very fast, then the relative speed between the black hole and the gas is very high, and then gas accretion will be prevented. Therefore, the black holes will have difficulty accreting gas. Sometimes black holes, which are still small, will be kicked out of the central region. When that happens frequently, and black holes will not have enough chance to gain or the mass. Whether it's real or not, we are not really entirely sure, but we thought at least we needed to improve on the agreement between the observation and the data. So we tried to do some calibration to improve this by changing some black hole related ingredients. But really, as I can tell you later, we didn't really have much success so far. And there are other issues. For example, we don't have barred galaxies. This is a really a critical issue. And then we don't have resolution test. So referees continue to tackle us regarding this issue. And then we don't have chemical elemental evolution, element by element evolution. So unlike the modern trend, that give you varieties of the resolution tests, we don't have that. And the element by element evolution, we don't have that. We only have Z. So we needed to do something. This is really cool, right? To have thick disk, thin disk, halo, dwarf galaxies for one Milky Way-like galaxy. If we can resolve all these elements by element evolution, that would be really nice. So we decided to run a new simulation called New Horizon 2 because I didn't know what to call it. And the code was rewritten by Sun, heavily modified so that now it works on the OpenMP. And then we have done some calibration to work with this new version and then to improve upon a few problems I have just talked about. And Jinsu worked on the chemical evolution. And then Tae-sun gave a lot of feedback to us, not only just on the stellar feedback, but also on overall feedback. And Yohan Kim contributed a little bit on the OpenMP side in the beginning. And then Marta, Yohan, Christophe, Corentin, and Sebastian all have contributed to this. The run is almost identical to New Horizon, except that the resolution is twice poorer, right? Compared to New Horizon, it's now poorer resolution, so that now we can run in roughly about a year. Otherwise, it's very similar. Stellar mass resolution similar, dark matter resolution is the same, and so on. We use OpenMP, so 480 in MPI domain and 8 threads, so altogether 3800 as opposed to 4800. So we have substantially fewer cores, but speed is probably about 50% faster than before. And I don't have time to go through the physics, so probably I will wait for another chance, maybe a few months' time when when New Horizon 2 is completed. I can discuss the results more. And we introduced chemical elements: hydrogen, deuterium, helium, CNO, MgSis, Fe. And also in the previous version, there are refinement jumps at a few scale factor, at a few scale factors. So there are discrete jump in terms of star formation history. This is unphysical, of course. So we had to change that to a smooth distribution of the refinement rather than the discrete distribution. Current status, it started in March, and now it has reached about 0.5. And snapshot steps are about 600. And we actually, by the way, maintain the same snapshots as New Horizons so that the comparison will be easy. Overall, due to the higher stellar feedback we employed, overall star formation rate history is depressed compared to New Horizon. And the current expected time of arrival is the end of December. It will be probably delayed by about a month because there is another smooth jump of refinement at about A equals 0.8. That's about it. And the first morphology, New Horizon and New Horizon 2 and New Horizon for the same galaxy identified through DM particles. and at the same epoch. And as you can see, the morphologies are very different. We are really interested in this, and we are working on it, but we haven't done enough to present any science on it. Just as you can see, just a lot of difference between the galaxies. And star formation main sequence is maintained all right, nothing to comment on. And stellar mass over halo mass relation has improved just slightly. So the orange band is the previous New Horizon, and the blue is the New Horizon 2. So as you can see, it has improved just slightly. And the black hole hasn't improved at all. New Horizon versus New Horizon 2, we don't see any improvement. And I can talk hours and hours on this. In the calibration, it worked fine, but in the real simulation, in the whole entire volume simulation, we didn't see the thing we expected from the calibration. So we are really puzzled at the moment. Chemical evolution, there are all the other elements, but here just focus on the Mg over Fe, so alpha element over ion. And this is the sequence. And this is the Milky Way sequence. It's not really a fit at all. I just draw any random line, and there are a lot of stars above it. And the same line now appears here. So it's pretty good. It's really as good as it gets. If you have done chemical evolution for entire galaxies, you will know how difficult it is to achieve this sort of agreement. And the second part of my talk will be on the YZX2. It's a cluster simulation.
So you have
yes.
3 minutes left.
Okay, I have only 3 slides left. So YZX2 is cluster simulation, unlike the New Horizon. It's focused on cluster. So previously, we ran 16 clusters using the Horizon AGN physics. And we have done a lot of interesting stuff, including RAM pressure stripping. But now it lacks resolution. So we needed to do something similar to New Horizon 2 using the same code for the same resolution, so same ingredients and so on. And the cluster mass is about 4 times 10 to the 14 solar mass. Currently, it's running on Rome in France and at 0.3.7, and it's about here. So this is the best spatial resolution versus the halo mass. The current best cluster simulation, for example, YZX, my simulation, Cluster Eagle, Romulus, and these curves are the ISO computer resources line, and you have New Horizon 2, and YZX will be here. So for the given available time, it'll be really the highest resolution of all. And when we have this done, we will be able to study like jellyfish galaxies and then the ultra diffuse galaxies, yeah, and so on. So the prospect is New Horizon 2 simulation is getting done now. It'll probably be done in the coming January. And
yes, are you still waiting for this share too?
I beg your pardon? I beg your pardon? Somebody was telling me something. YZX2 will be done about a year from now because it's still in the embryonic stage. And as a service, our team is trying to provide the code Ramses Yomp. It's an OpenMP version of the code, which is being used by Sebastian, as I know, and also perhaps Yohan. And then as the next speaker will say, that Jinsu will give us the new galaxy and halo identified using the 60 code Velociraptor. And then we are making a whole bunch of SCUT images on the New Horizon galaxies, not only using the SCUT software, but also using the simpler code made by JK. And you will hear from them directly soon. Thank you very much. I'm done.
Thank you very much, Sukyoung, and for keeping the time. So I think we have already one question from Hugo.
Hugo?
Hello. Thank you very much for the introduction of New Horizon 2. It's a shame that you still cannot reproduce the black hole mass, halo mass. So you said that you had some differences between the black hole models between New Horizon and New Horizon 2, and you didn't want to get into the details. Can you get into the details so we can try to 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 understand why
okay,
it's still not working.
Okay, I'll give a short version, and the real short version is you really need to talk to Han San, my student, San Han. He's working on this, so he can tell you more detail. To give you my short version of the answer, we don't know. In the calibration, it seemed to be working all right. We were able to put the black hole at the center of the galaxy through the calibration simulation. But when we use the same parameters in the whole simulation, it didn't really work out. So galaxies still get kicked out of the central region. Just
but my question was more, what are the differences? So if you have made a calibration, it means that you have changed stuff with respect to your horizon. So I was just
yeah, there are a few changes. Basically, we tried different values of diffusion, friction, dynamical friction, gas, stellar, and so on. And also we increased the black hole seed mass as well. And a few conditions in the central region in terms of the stellar feedback and so on, AGN feedback and so on. And we are very happy to discuss the detail, but probably not during this my talk, and San can actually.
Yeah, sure. Okay. Thank you very much.
Yohan, you have a question?
Yeah, thank you, Sukyoung, for this nice talk. About the chemical tracks, can you go back to these? Nitrogen seems to have an issue, right? It's because of the stellar yields that have been used, right? In principle, if you don't have a stellar rotation in your stellar yields, it usually produces this kind of underproduction of nitrogen. Do you think it's the problem?
And carbon as well. Yeah. Yeah. I don't know. We just got these plots and we haven't really had time to digest these plots yet. Carbon seems very weird, and nitrogen also. But we try to find empirical data for the entire galaxy carbon measurement and nitrogen measurement, and it was very difficult to find one to compare. So yeah, it seems weird so far, but yeah, give me a little bit more time, then I will probably be able to say something more. I'm much more focused for now for the alpha element, oxygen and Mg over Fe, because these two elements are very well constrained observationally, and they are widely used for population studies, and that's exactly why we are doing this.
So I guess we have time for one last question. Amandine, you wanted to ask something?
Yeah, I'm going to change scale slightly. Thanks, Sukyoung, for the really nice talk. Can you say a tiny bit more about the cluster simulations? Did you make some adjustment to the AGN feedback scheme? Because it's known that the gas content in clusters tends to have problem with current implementation in Ramses.
You are asking a very good question. It's very painful question to me, because we are using the same Ramses code that we are using for NH2, New Horizon 2 as well. And then for
where you cannot test cluster scales.
Right, but and also in New Horizon 2, we already see that our prescription does not help black holes centering at the galaxy center. And so that's a big problem for the cluster galaxies, because for the cluster galaxies, AGN feedback will be much more important than the field galaxies.
I'm also talking about the global gas content within R500, which tend to be too high. Basically, the AGN feedback tends to be not efficient enough in current implementations.
Okay, that I haven't thought about it. I mean, I'll be happy to discuss that offline if you can tell me a little bit more. Yeah.
did you look at what they look like in Y6? That would already be a good starting point.
Yeah, so what exactly do you want me to look at?
We can chat offline.
Okay.
That will be better.
Thank you.
And
Okay, I think we should move to the next talk. So thank you very much, Sukyoung.
Thank you.
And now I would like to invite Jinsu to share his slides. Great, thank you. So now we listen to Jinsu Rhee, who is going to talk about a six-dimensional galaxy finder for high-resolution simulation. So Jinsu, I will give you a warning 3 minutes before the end of your talk.
Okay, do you see my slide?
Yes.
Okay, good. Hello, everyone. Hi, I'm Jinsu Rhee, a PhD student from Yonsei University. Thank you for giving me an opportunity to share my result and apologize for my title being changed in the last minute. My new title is the Performance Enhancement of 6D Friend-of-Friend Galaxy Finder for high-resolution simulations. Structure identification is a very important step to analyze cosmological simulation data. Historically, there are two main streams of how halos or galaxies are identified: SO-based or friend-of-friend-based method. The SO-based method finds structures based on the local density of particles where particles are clustered if their local density is greater than the threshold value. On the other hand, friend-of-friend method relies on the proximity among particles, in which particles are clustered if their distance is less than the predefined value, linking length. In this work, we focus on the friend-of-friend galaxy finder. The most important reason why we target the friend-of-friend galaxy finder is that it has expandability to higher dimensions such as phase space. Many galaxy finding codes are limited to using positions of particles only, and it's more and more required to use velocity space of particles as well to find reliable substructures within high-dense region. To expand to phase space, an FOF algorithm only requires the definition of metric in 6 dimensions, so the phase space information of particles can be readily considered. Yet, it's still challenging to find FOF systems with their phase space metric, mainly due to its cost expensive calculations on high resolution simulations. The FOF method basically needs to calculate distance among particles, so that it's very computationally expensive when it performs on overdense regions. Thus, our aim of this study is to perform 6D galaxy identification on high-resolution simulation within a reasonable human time. For the 6D galaxy finder code, we use Velociraptor STF. The code finds 3D and 6D FF halos of galaxies and are able to read various input types from Ramses gadget to other data type. The code provides multiple types of searches, for example, both or either using dark mirrors, dark particles, and or gas data. For the sample simulation, we use the New Horizon simulation data. New Horizon has unreached high resolution compared to other cosmological simulations, for which spatial resolution is about 34 parsec and stellar mass resolution is 24 solar masses, both allowing the central density of galaxies to be very high. Thus, performing galaxy finding with Velociraptor on the New Horizon simulation is a good test for galaxy finding for the next generation of cosmological simulations. Velociraptor finds galaxies with multiple steps. First, from the raw data, it finds 3D FF. Within its 3D FF, here the left shows just one big 3D FF. The code finds 6D FF this time with using smaller linking lengths. Here, the color density shows individual 6D FF within the 3D FF. And then in each 6D FF, the code identifies galaxies by catching dynamically cooled cores and assign particles to the cores based on their 6 metric to the cores. Because many codes use different ways of define galaxies from the larger host, we limit our analysis to 60FF only and investigate how fast the 3D and 60FF groups are searched. As the first step, we ran Velociraptor on the New Horizon simulation at the snapshot with redshift of 2.46, where the number of stellar particles is about 47 millions. What you can see from the left figure, which is well clock time for searching 3D and 60FF as function of their particle numbers, it is very slow. For the most massive 3D and 60FF object, it takes more than 10,000 and 1,000 seconds respectively. Both findings also show very poor scaling proportional to the number of particles, power over the number of particles, which means it will take unpractically long well clock time to search galaxies massive than 10 to the 11 solar masses. We expect such a slow speed is mainly due to too many distance calculations at the core of galaxies. Actually, many friend of friend codes optimize distance calculations using the KD tree implementation. KD tree is a simple binary tree of particles with which a domain is divided into the two subdomains. For example, the left figure shows the whole particle distributions, and it's divided into the two subdomains like this, and then each subdomain again divide, and so on. The advantage of KD tree implementation is that it effectively reduces the number of distance calculations finding particles within the linking lengths. Without any implementations, big O and square computations are required. With KD tree implementation, however, in usual case where the linking length is comparable or smaller than the size of node, a few distance calculations of particles just in one or two nodes are required, scaled with big O and log n. On the other hand, in the extreme case where the linking length is much longer than the size of node, where often happen with high resolution simulations, there will be many nodes within the linking length, resulting in many distance calculations for each particle scaled with n square, n core square. Unfortunately or fortunately, New Horizon is that case. These three panels shows the most massive 3D-FF group of New Horizon, 3D-FF group in the New Horizon simulation at the snapshot of redshift 2.46, in which the group has 4 million stellar particles. At the central region, with box lengths of 6 kiloparsec, there are 3 million particles, which is 70% of the total particles. The third panel shows the same plot with the middle one, with linking length, sphere, and the KD tree nodes drawn together. For the particle located at the center, there are 1.6 million particles within the linking length, and 70,000 nodes within the search sphere. Thus, about 40% of the total particles are located within the search distance of just one central particle. To reduce such a huge amount of distance calculations at the central region, we devised several implementations. First one is node closure scheme, which close node if we don't have to compute distance for the particles within the node. It happens when all particles in a node are connected to an FF group. For example, the right figure shows the particle distribution with their KD tree node drawn together. For the particle here, after searching particles within linking lengths, all particles in this, and this node are connected to this particle, which means that we don't have to open this node any further. So we close this node so that they are no longer opened for other particles. This way, KD tree gets shallower as finding FF groups. Indeed, this scheme is already implemented in other most of FF-based code. The second implementation is node geometry scheme. The idea is that if a node is fully inside or outside such a sphere, we don't have to conduct distance calculations for this node. We develop a cost-effective way of determining such a geometry criterion. Thus, every time a node is visited, a simple calculations is performed where distance calculations in that node will be performed or not. The third one is SPLAY. SPLAY has an aim to effectively find member particles. For example, after finding neighbor particles for this particle, we have to repeat the same process for one of the connected particles, colored point here, to check whether there are other particles to be connected. If the next particle is chosen to be one of close one, a few member particles are connected because many particles within this such sphere are already connected to the previous one. In contrast, if we can choose one of the most distant particles, there will be more particles to be connected, which means member particles are effectively found. Again, we implement a cost-efficient way of finding such distant particles. Then we see whether its implementation works well when applying alone. The left figure shows the work clock times as a function of friend-of-friend particles for the 3D FF with a single implementation applied alone. The upper panel shows the speed improvement compared to the original execution, where 100 means 100 times faster than before.
Jinsu, you have 3 minutes left. Sorry to interrupt.
Okay. For the 3D FF result with node closure or node geometry, the performance is impressively updated, being about 100 times faster than before. Yet, SPLAY operation, here science points here, shows no improvement at all because the single implementation of SPLAY does not affect the number of distance calculations required. Thus, considering that single implementation of node closure or node geometry has significant performance update, the origin of poor performance for 3D FF search is due to repetitive visit to already fully connected nodes. For the 6D FF result this time, no single implementation shows significant performance update. This means that our implementations are not optimized for higher dimension, often called the curse of dimensionality problem. To understand the curse of dimensionality in the friend-of-friend algorithm, we bring a simple example. Suppose we want to find particles within the linking length B for the centered particle in a box with a length of 2B, where all particles are uniformly distributed in the box. For the one-dimensional case, all particles will be connected to the center particle, whereas for the 2D or 3-dimensional cases, some of the particles are connected. The fraction of a connected particle to the total particle is corresponding to the volume fraction between the sphere and the box. The fraction can be generalized in n dimension, which approaches 0 as dimension goes higher. For the sixth case, the fraction is about 0.08, which means only 13 spheres are required to fully cover the hypercubic 6-dimensional grid. Thus, in higher dimension, many visits are required for a node to be fully or a node to be closed. In our investigation, the curse of dimensionality seems to be partially solved when we apply all implementation at the same time. When we apply all 3 implementations, we achieve a roughly 6 to 10 times faster, 6 times better speed than before. This is because SPLAY operation finds member particles effectively, which means a node gets closed with fewer visits, and the closed node is no longer visited by the node closure algorithm. Finally, we bring the final performance result of using all implementations. Left figure show the well clock time figures with original and updated result drawn together. We note that final result well follow the ideal scaling relation and log n shown as dotted lines here. The speed improvement is about 10 times, 1,000 times faster for the 3DFF and 10 times faster for the 6DF. So now it's feasible to find 60 galaxies in the New Horizon simulation. For the all consecutive 800 New Horizon snapshots, we successfully find galaxies and halos with 60 FF, and their model trees are built as well. And we note that a new New Horizon catalog is now available. I'll leave my conclusions here and take questions. Thank you for listening.
Thank you very much for this fantastic work. Do we have questions from the audience? So Jan, you can ask your question.
Thank you very much. Yeah, for this nice talk on the impressive acceleration of the code. Yeah, I'm just wondering, how do you deal with the usual friend of friend issue like bridging, and also how do you define the linking lengths in velocity space? I mean, how do you which linking lengths do you take in velocity space? So
yeah, usually the linking length for velocity space is defined as the dispersion of larger host. And velociraptor use iterative way of defining velocity dispersion for the host system as finding smaller and smaller systems.
Okay.
Kuro?
Hi, Jinsu, great talk. I've tried using Velociraptor myself, and I was wondering you could help a little bit. Firstly, are you using the Rodrigo Cañas version of the Galaxy Finder?
Sorry?
Are you using Rodrigo Cañas version of the Galaxy Finder, or just the original Velociraptor Halo Finder, but in galaxies? Because I know he did an update for just galaxies with a little bit of an improvement. And I was wondering if you're using that on that version.
I guess I take the code from the latest branch of Velociraptor, but I don't know this is from Cañas version or not. So I will check that.
Okay. Okay. And then you use using the dark matter particles and the star particles. You're not converting the gas cells into particles, right?
Yeah.
Okay. All right. Okay. Thank you.
Okay.
So we have time for one more question, if there is one. Otherwise, let me invite Yohan to share his slides. And thank you again, Jinsu, for your talk.
Okay. Can you see everything well?
Yeah, thanks, Yohan. So Yohan is going to talk about dust in simulated galaxies with Ramses.
Okay. This is much work in progress. Simulations are still running, but the code is there. So I will introduce what we have been doing recently with to include dust as a separate species in Ramses for galaxy simulations. First of all, why should we care about dust? So dust is an important thing for many problems in galaxy formation. It is a problem for estimating star formation rate, especially in the UV, and also the detection rate of galaxies, especially with the context of JWST. Dust is also a confusing factor when people try to estimate gas metallicity, because some metals are locked into dust. It's an important problem for coupling radiation as well to the dust gas phase mixture, and thus is involved in other processes such as chemistry and cooling for the SM. And of course, when when dust is estimated in galaxies, it's also an indirect way of understanding how galaxies evolve at different times in the universe. So the dust model, so we have a few assumptions I will explain. So first of all, we assume that dust moves together with gas. So in other words, we say that the stopping time is very small compared to any gas dynamical time. So the good thing is that we can treat dust as a passive scalar, just as we do usually with the metal gas phase, and we only follow two major dust constituents, which are carbon and silicates, and two dust sizes, small grains at 5 nanometers and big grains at 0.1 micrometers. This is an approximation. We're not following the whole grain spectrum, but apparently, according to Hirashita, this is a fairly good approximation, at least for a galactic context. So this has been included in the Ramses Yonsei OMP version of Ramses, and this has been also tested with reducing a bit the size of the problem with less chemical variation, or with just one grain size, etc. But I will show you the full problem. So the various dust processes are the following. It's well summarized in this little cartoon I took from Granato and collaborators. There are several processes affecting the dust in the simulation. This include accretion of metals from the gas phase to dust phase, the ejection of dust through stellar ejecta, and also destruction of dust because of supernova explosions, and shattering and coagulation, which transfers mass from one size to another, and finally the thermal sputtering, which is just high temperature gas particle which erodes progressively the dust grains. So step by step, we have included dust in stellar ejecta. So for that, you need to assume an initial mass function, some isochrone H tracks for stars, some stellar yields, and then finally a dust condensation efficiency. And when you have that, you have your input stellar yields, stellar dust yields as well, and this is validated at least for the chemical part, not for the dust, for the chemical part through galactic chemical evolution models. I just show you very quickly this, but you see the chemical tracks here. And the other step is to have a supernova destruction of dust. So for that, you assume a set of solution. You say only explosion with velocities larger than 100 kilometers per second is able to efficiently destroy dust, and the reason for that is linked to the sputtering process in the ejecta of stars, which appears roughly above this velocity. So this is modeled in the code. So let me skip you the details. And the other step is to have dust accretion. This is a very key process. We'll see that later. To have dust accretion from the gas phase to the dust phase, and this is set up by this accretion time, which depends on basically the gas density, the metallicity of the gas phase as well, and temperature, and through the temperature, the sticking coefficient that you see on the bottom left of this slide, which is a function of the temperature. Okay, and we'll play a bit with that. I'll show the effect a bit later. The other process is the destruction of dust through thermal sputtering. So when the gas is at high temperature, so basically at above 10 to the 6, a few 10 to the 6 Kelvin, which correspond to a sound speed of 100 kilometers per second. So this reminds you of the effect of supernova destruction, which is just inertial sputtering instead of thermal sputtering. So thermal sputtering happens above this temperature. This is modeled with this time scale, as you can see. And the other process that happens at the same time than thermal sputtering at high temperature is cooling. So when electrons collide with dust grains, they give their some momentum to the dust grain. They lose velocity, so sound speed, and they decrease their temperature. Some of this energy is radiated away. So it's effective cooling for the gas phase. because of this process. And the actual trajectory is shown on the bottom right through the red line. So when you have both dust gas cooling and thermal sputtering, that's the red line that is followed. So this is an efficient cooling process, but because you destroy dust at the same time, this is not so efficient, right? You very quickly converge to the classical gas cooling, but this can be an important process still for say galaxy clusters, for instance, for the intra-cluster media. So the other important process for dust is dust shattering and coagulation, which is a process transferring mass in the dust phase, right? So this is just transfer of mass between grains. So shattering is happening in diffuse phase of the ISM, so typically below a particle per cc. So it's big grains that collide together at high velocities, typically above kilometers per second, and which shatter into small fragments. And you have the typical shattering time. So it depends on the dispersion velocity of those grains. We don't have access to this quantity directly, so we assume some value. Okay, it's not measured in the simulation. This is just a value we take. We take 10 kilometers per second for big grains. Okay, this is a clear limitation of what we can do, but we are exploring something about that, but I won't show it today. Okay, and the other process is coagulation, which happens in the dense phase, so typically above 10, 100 particles per cc. This requires low velocity for the small grains, so basically below kilometers per second, even below 0.1 kilometers per second is more realistic. And again, we assume a given fixed velocity dispersion. Okay. And okay, so now I will show some results of this implementation and exploration of dust evolution. So the simulation is an isolated disk simulation. Just to start with a disk of gas and stars and the bulge component. There's no cosmological context in there. So we start with a halo mass of 10 to the 11. Stellar mass is twice 10 to the 9 solar mass. It's a prominent disk. There's half of the baryon mass locked into the gas, and we explore different initial gas metallicities. We start with solar composition of elements, carbon, nitrogen, oxygen, iron, etc. We have a given small dust to metal ratio initially, just to avoid to be strongly affected by this choice. We split the dust into half small grains and half big grains, and you see the typical refinement resolution we have. We reached 20 parsec resolution. We have a test at 10, but I won't show it. And finally, the physics is quite simple. It's gas cooling down to a minimum temperature of 10 to the K. No polytropic equation of state, very important, especially because of coagulation, shattering, accretion to dust. If you modify the temperature, modify those timescales. So no polytropic equation of state, and a Schmidt law with constant star formation efficiency and type 2 supernova feedback using the mechanical implementation from Tess and Kim. We have also stellar winds in type 1A, but they are fairly irrelevant. You'll see it later. So a movie, just to have a nice introduction to what's happening. So you see a projection on two bottom rows and the slice. We'll do it again. On the two, projection on two top rows and the slice on the two bottom rows. And you see the gas density, temperature, dust to metal ratio, the fraction of small grains, fraction of carbon grains, and that's interesting to see that small grains are decreasing over time in the disk and also in the wind, and we'll see some consequences. Let me skip that one, and now we can do some. I can show you some profiles of the dust to metal ratio as a function of temperature, density of the gas, and so in different regions of the galaxy. So on the bottom left, you see this dust to metal ratio in this temperature density diagram in the central regions. Of course, the dust to metal ratio is the largest in the dense and cold regions, and you see that the various distances from the galactic center, but this DTM is decreasing with distance to galactic center because there are less and less gas. The gas density profile is a decreasing function of radius, so this is expected, of course. This is the fraction of small grains. So small grains are the fraction of small grains is larger in the ISM than in the wind, which is the hot phase and hot diffuse phase, of course, where because of thermal sputtering and supernova explosion, which destroy the small grains more efficiently. And this fraction of carbon grains. Let me skip that one as well. Okay. So now this is the dust to gas and dust to metal ratio as a function of time for 3 different initial gas metallicities. And you see, there is a very strong effect of the gas metallicity on the DTG, dust to gas ratio. What you see as a pink line is the observational constraint, and the black line is the black solid is the actual measurement from the simulation. And indeed, we see this increased value with metallicity. And the reason is that accretion of metals onto dust is directly proportional to metallicity. Right? The larger the metallicity, the faster the accretion process, and this naturally increases the dust to gas ratio. And you see also as details here the fraction of small and large grain carbon silicate. This will be useful for just a couple of slides later. Okay, so now we can wonder which dust processing dominates the growth of dust or destruction of dust. So let's focus for a moment in the middle column, the metallicity of 0.8 solar metallicities. And you see that accretion is an important process that dominates over supernova destruction, which is in pink, dominates over the supernova production, thermal sputtering, sorry, and supernova production, right? So accretion is setting the value of dust to gas ratio, and an important thing is that shattering is more efficient than coagulation in here. And of course, when you change the metallicity, you see the things are changing a bit, right? Accretion is not so dominant anymore. Supernova destruction.
Yohan, you have
Yes.
3 minutes left. Sorry.
That's perfect. Thank you. Accretion is becoming more and more comparable to supernova destruction, supernova production, thermal sputtering as well, and shattering is still much larger than coagulation. It's even larger than before, and this translates into, of course, more small grains because shattering is creating the small grains in the ISM, transferring mass from big grains to small grains. Okay, and the opposite thing is happening at higher metallicities, but let me skip that one as well. So now, can we do better? Can we do more with this in terms of observational constraints? So one thing that is interesting is this 217.5 nanometer bump in the extinction curve of the ISM of gas in galaxies, and we can do a prediction of this by using the distribution of sizes of grains and their composition, depending whether they're carbon or silicate. They don't have the same extinction law, which is QX in this formula on the top left. And this is the result on the bottom right is the extension curve. The points are observational data for Milky Way, SMC, LMC. And our galaxy should resemble a bit the Milky Way. It's lower mass, but the same metallicity. So there are good reasons to think it should resemble the Milky Way. And you see that we nicely reproduce the bump, and this bump is due to carbon grains, and in particular, the small carbon grains. Okay, so I think it's an interesting success and prediction from this model. And if we play a bit with parameters, especially with coagulation, for instance, we change the threshold at which we allow for coagulation. Instead of 10 particles per cc, we decide coagulation happens at higher density, at 100 particles per cc, and we change slightly also the velocity dispersion. You see completely the bump is completely overshooting the observational data. There are too many small carbon grains compared to observation. So that's a way to constrain directly the parameters for coagulation. And I will finish on that one. The effect of the parameters entering the accretion, in particular the sticking coefficient, which is not very well known. The red line is observational, not observational, sorry, lab experiments, but not it's using molecular hydrogen on grains and not metals. It's different densities, etc. So it's interesting, but we are not doing the same thing as astrophysical gases. And the green line is our fiducial model, which is more theoretical prediction, so for what it's worth. But you see the effect of changing this sticking coefficient. This naturally changes the dust-to-gas ratio, the dust-to-metal ratio, and also the depletion factors of the various metals. And this seems to favor the Le Bourlot sticking coefficient to reach the dust-to-gas ratio. And even with that one, we're a bit on the low side of the observational constraints. And I will just finish on this, the conclusion. So the MRN, so the Matisse size distribution of the ISM, Milky Way ISM is nicely reproduced because of coagulation. The dust-to-metal, dust-to-gas ratio are a bit on the low side. Probably the sticky coefficient needs to be increased a bit. We need to investigate how these DTM, DTG evolve with gas content, halo mass, and especially in the cosmological context. And these are just some, so the last two ones are just random thoughts about nice applications of dust, in particular for thermal instability in the intracluster medium. I think it's an important thing. And the second step, I think that we'll try to do is try to couple the radiation to this dust component. I'll finish on that.
Thank you very much. So we have several questions already. Maxime, do you want to ask your question?
Yeah, sure. I think I was last to raise hand, but thanks anyway.
Go ahead.
I was just wondering, Yohan, have you started to look at how much dust you have in the outflows? Because in the simulation, like in the movie you showed, there was clearly outflowing dust. And I was just wondering if you have any constraint on like the loading factors in terms of dust or that kind of thing, because there start to be some observation of dust-enriched outflows, right?
So simple answer is no, I haven't done anything about the wind part. I'm just focusing at the moment on the SM because this is where there are the strongest constraint. But of course, yeah, the wind part is interesting. We always, right, in general, when we paint dust onto galaxy simulation in post-processing, we always assume that the DTM, dust-to-metal ratio in the hot diffuse phase is 0, which when you look at those simulations, is clearly not the case, right? It's small, it's not 0.4, it's not the usual values, but it's 0.1, it's not negligible at all.
Julien?
Yeah, Yohan, I had a quick question about the extinction curve. When you said you matched it for the Milky Way, did you manage to suppress the bump and get a steeper slope when you reduce the metallicity?
Oh my God, this is a terrible question. No, and actually it's I don't know how to suppress the bump. To suppress the bump, it's easy. When you see the decomposition here, you just remove carbons. If you remove carbon and small carbon grains, you remove the bump, right? You can play analytically with that, no problem, it's easy. But how you do that in the actual simulation, I have no idea, because the small carbon grain, they always quite grow. I didn't find a way to suppress them. That's the easy answer.
Yeah, so and my follow-up question was, do you think this has something to do with the fact that these small grains are not in thermal equilibrium, and so they should be treated a bit differently in what you're doing?
Maybe. Yeah, I'll be happy to discuss that later.
I think we can take Astrid's question.
Hi, Yohan. Very interesting. Coming back to your dust to gas ratio plots, so you're always underestimating the dust to gas ratio with respect to observations, I remember, but you also have a strong tendency with metallicity. Maybe you said why, but can you explain why?
So if your question is about why the DTG is increasing with metallicity, the reason is very straightforward. It's there. In the accretion timescale, you have a dependency with the metallicity. as you can see, inverse dependency with metallicity. So if metallicity is larger, the accretion time scale is smaller, so you accrete faster, and the dust content increases.
And so that is sufficient to explain why your model works reasonably well at high metallicity, but fails at low metallicity. That's the only reason.
Yeah, but you see the trend is not the same, right? It's not the same than in the observation, right? At super solar metallicities, we are okay with observation. At solar, it's barely there, and subsolar, it fails.
Yeah, exactly.
Right. So the DTG versus Z is not the same than in observation.
Okay.
So I don't know why yet.
Okay, thanks.
It's a very simple experiment we're doing here, right? The galaxy is the same. We're just changing the metallicity. So changing the metallicity probably change also you should change at the same time the properties of the galaxy, the disk extent, the gas to stellar mass ratio, these kind of things, right? They are not the same. We just change one thing.
Okay. Thanks.
Maybe so we can maybe take Hugo question if it is very quick.
It will be very quick. I just wanted to say first very nice talk. I wanted to say that you might find your happiness in Hormel and Cousy's paper for the drift velocity, where you have an expression where the dust couples to smaller and smaller to say vortex in turbulence cascade. So it might help you, I guess, and you might be able to deal with more beans using that. And,
so actually, just to answer, we actually have recently implemented that, what you mentioned, but but the simulation is still running.
Yeah, okay. Well, maybe we can chat after in the coffee. Yeah.
Thank you very much, Yohan. So let's move to the last talk before the break with Loic.
Yes.
So Loic is going to talk about light AMR standardized data structure and associated lossless compression algorithm.
So do you see my screen?
Yes.
Okay, great. So I'm Loic Strafella. I work for the CEA as a PhD student, and I will give you a technical presentation of a new EMR from R that we call the light AMR, and I will also present the different algorithm we developed upon this light EMR from R, and I will present benchmarks on Ramses datasets. So first of all, it's a collaboration between different laboratories of the CA with different kind of skills. We have on one side a Ramses community, of course, and with a community of PIMSES developer, which is a post-processing tools for Ramses outputs. We also have on the other side a team that work on parallel IO, and also a team that work on the visualization algorithm for tree-based EMR that is called VTK hypertree grid. You can find a link there where there is an introduction to that VTK new data structure that I will mention later on the presentation. So the main objective of our work is to improve the Ramses scalability. We already improved the Ramses IO bottleneck by the integration of a parallel IO. And we also work on the Ramses scalability, but more indirectly, in the sense that we are working on reducing the size of the data volume that each Ramses snapshot produced. And to do so, we introduce a new way to describe the EMR grid and the data, and it's called the light EMR. And we built, so upon this light EMR, different kind of algorithm to reduce the data size of the snapshot. So just to give you a little spoiler on the results, we are able to reduce on a big simulation that is called Extreme Horizon. We have the link at the bottom of the slide. So we were able to reduce the size of one snapshot regarding the EMR and the hydrodynamical data from 2.8 terabytes to 1.7 terabytes, so saving more than 1 terabyte of this space. So to do so, we introduce the light AMR for tree-based EMR. So if you take a small example and look at what Ramses outputs in this kind of example, you will see that in the output EMR routines, Ramses will output several integers arrays and float arrays, and just to describe the AMR data structure. And in a simulation like Extreme Horizon, it could lead to 500 gigabytes just to describe the AMR grid. So what we did actually, we don't see the picture, but it's actually the same picture. So we use a Boolean array instead of integers array, and we only use 2 arrays to describe the AMR grid. So we use an array that we call the grid refinement, which is kind of the equivalent of the father-son array from Ramses. We use an on-off-chip mask array, which is kind of the equivalent of the CPE map. And then we use a very small array just to describe the number of cells per levels. So it's kind of annoying that we don't. Do you see the picture of the tree? No.
No.
I will just restart maybe. Okay, don't want to show but this is, sorry. I will just take the PDF version. So we had to introduce some convention to the light AMR in order to describe the AMR grid. So the convention is quite simple actually. For the grid refinement array, what we did is we set to 1 if a cell is a core cell and 0 if it's a leaf. For the grid refinement, for the ownership mask, we set to 1 if the cell does not belong to the current MPI process and 0 if it belongs to the current MPI process. And to process the tree, we go from the top of the tree to the bottom, and we use actually the Z curve to move through levels. So in this small example, this is the light AMR equivalent of the description for this grid. For in red, the first domain, and in blue, the second domains. So just to make it short, for the first cell, since it's a core cell, then we write 1, then we describe all the cells of the level 1, then all the cells of the last level that are all leaves, so all zeros. We need to do some correction on the ownership mask, just to be sure on the visualization side that if we process some leaves that belongs to a current MPI process, the father cells also belong to the current process because we will move recursively through the tree and we will make some shortcut in case a cell does not belong to a current process. So we need to make this small correction. For the scalar field data, we actually use a simple mapping, a 1-for-1 mapping. So if there is a cell that is described in the grid refinement, we just add the scalar field data that correspond to the cells. So once we describe this light AMR tree, we then built 3 algorithms to remove and compress that light AMR data structure. There is one for data redundancy. Actually, if you take back this example, you can see really easily that these cells on the right doesn't bring any more information to the MPI process in red. And it's the same for T cells in red for the process in green. And then there is 2 lossless compression algorithm that we developed, one for the grid refinement and the ownership mask, and one for the floating point scalar data field. Either there are simple precision or double precision data. One important remark is that all those algorithms were designed and optimized for the light AMR. This is what explains the height compression ratio that I will show you later. So for the tree pruning, as I mentioned, you can see that if you describe the light AMR of the first domain, the T cells doesn't bring any more information to the domain in red, and it will be described in the second domain in green. So we can remove its description by saying that it's no longer a refinite cell, but just a leaves. And then you can see already that he removed the associated scalar field data. And we also applied the same correction of the ownership mark to be consistent. And if we take a look what are this algorithm brings to some real data sets from Ramses. So we took 3 simulations, 3 urban simulation that are zoom simulation and extreme horizon, which is a cosmological simulation. So we see that on free Galourian simulation, we were able to remove 38 and 26% of the cells of the AMR tree, and only 11% of extreme horizon, but on the volume of data, it still represents a large number of cells. So now the lossless compression. So once you have built the light timer, reduce the redundancy in the light timer tree, you can go to the second step, which is how to compress the light timer description. So the first algorithm that we call the CPS52 for continuous pack size base 52 encoding, it's just a way to compress the grid description and the ownership marks using a level by level compression, which means that it's also compatible for post-processing with level of details approach, where you can only uncompress a certain number of levels. We also developed a small algorithm that allow us to manipulate directly the compressed stream with a small overhead and with some forward access when you try to access to the value of a cell. Another important point for Ramses is that this algorithm is really memory friendly. For the double and super precision compression, we use an algorithm that is called father-son predictor, which is a lossless compression. So there is definitely no loss of information when you uncompress the field. It's a very fast compression and decompression, as I will show in the next slide. And of course, it's also memory friendly. That was an important point to use within Ramses. So for the CPS52 compression, the general idea is quite simple, actually. We will just compact the size of continuous successive zeros in one in the stream of the grid refinement, for example. And we will also insert some seeds at the end of levels. So we are able to uncompress until certain level. We also are able to compute some offset, etc. So to give you example of the CPS on the same data sets, you can see on the first column that we achieve quite high ratio. Actually, it's a little bit slower than the ZLib would do with the level 9, so the best compression, but we achieve much higher compression speeds than all the tested library that we use. And so even on extreme horizon, actually we achieve 400 megabytes per second. But if you take a look at the number of cells of in extreme horizon in the biggest domain, where you will see that there is 3 million of cells. So for a grid refinement array that is 1 Boolean, it's kind of 3 megabytes. So it's really fast. For the ownership marks, we achieve a really enormous ratio with high speed, but mainly because there is a large pack of zeros and one, so it's go really fast. For the FSP compression, the general idea is quite simple, actually. When you try to compress data, there is generally 2 main techniques that are used. The first one is an entropic encoding, where you try to find a pattern that will repeat itself in the stream you want to compress. This is, for example, how we compress text with enough Huffman encoding. But of course, with a float like a density field, there is no reason to find some pattern recurring in the fields. So the general idea is to use a delta compression, where you use some predictor or predicting function, mathematical function, to predict a value. And then what you do is you compute the difference between the prediction and the true value. And then this is the difference that you will encode. So what we did for the predictor is that we directly use the topology of the AMR grid. And by topology, I mean that we use, for example, if we take this grid refinement array, we'll use the value of a core cells as a predictor for the value of its sons. And so with some XOR computation, after having mapping the double precision on unsigned integer, we counted the number of leading zero for a pack of sun cells. And the compression occurs when we just take the resulting stream without the leading zero. So at the final stage, when we compress just a sun, all the sun cells with the fader value, what we do is we encode the number of leading zeros that we remove from the XOR operation, and then we put all the residue of the XOR operation.
So Loic, you have 3 minutes left.
Okay, thanks. So to give you, I will just skip this slide. So I said that we write first the number of leading zero that we moved. We use 4 bits to encode that number of leading zero. So it means that we limit ourselves to 15th removal leading zero that we can remove from the stream. Actually, it's because we noticed, if you take a look to this graphic, it's not important that you see all the information on the graph, just that in blue you have an encoding on 3 bits. So if we limit ourselves to 7 bits that we remove, then we will achieve that kind of ratio. But actually, if we just pass to 4 bits, we achieve much higher ratio, but there is no significant gain if we go to 5 bits encoding. So if we want to remove 31 at maximum or 63. So if we take a look at the benchmark on the same data, there is important number. So if we remove from the double precision representation the sign plus the exponents. So in double precision data, it's 1 bit, sorry, for the sign, and 11 for the exponents. We would achieve for double precision 121 of compression ratio. But what you can see on the auto simulation, if we generally, apart from the density field on Frigg, that we achieve this ratio, it means that we remove from the data all the exponents. This is kind of expected results, because it's the basis of EMR to avoid having too much difference gradient between 2 adjacent cells. On the right, you have the equivalence if we cast the field to simple precision. Donc you see that we achieve a much higher ratio. This is mainly due to the fact that the sign plus exponents represent a bigger fraction of the encoding on simple precision. And regarding the speeds, you can see that we achieve with a single threaded algorithm and a low frequency CPU a speed above 1 gigabyte per second, which is extremely high for compression ratio. Now that we have a compressed light timer, I will just show you that we are also able to uncompress it and visualize the data. So to do so, we use the VTK framework, mainly because it's supported by Kitware. So it means that Kitware is engaged to make the maintenance and also the compatibility of the VTK Pertugade with all the VTK filter. The VTK Pertugade, it's also kind of based on the light timer description. So it's also a memory-friendly data structures. And it's also provide cursor, which is a way to move through the VTK Pertugade easily. Of course, there are some drawbacks of using VTK. For those of you that have already used VTK, you know that there is a kind of huge complexity, but since we are working on post-processing tools, we try to make it as easier as possible. The community of users for the VTK Pertugade is not yet really large, but Kitware is doing a lot of communication around the VTK Pertugade, like I showed at the first slide, the introduction to the VTK Pertugade. So this is just a small image to show you that we are able to uncompress and construct the AML grid on a simple 2D blast. We're also able to map some domain, for example. Here you can recognize the Hilbert decomposition of the blasts. We can also make some more advanced geometrical filter. For example, if we add the density to the VTK Pertugade, we can also construct the VTK Pertugade around a given region, which means that on the white square there is no data that are loaded, but they are not constructed also. So it's a very compact way to visualize some geometrical data. We also already ported some splitting technique to make images. On the left, you have the equivalent using the PIMSES algorithm. And on the right, you have the equivalent version with the VTK Pertugade. We have some work to do yet on the units, etc. But the general idea is that we have the same image with a small rotation, but this is mainly due to the axis that we use for the plane. So it's not a problem. And this is just a small rendering of extreme horizon. It's not interactive, but we can construct some region with some domains, etc., etc. And just this is for the future. So we are still working on different kinds of algorithms for improving, again, the memory efficiency of the overall. We also are working on ray tracing, volume rendering, and raycasting. We already have some bricks available. We're just managing how to put it all together to have the final algorithm. And we're also working on a multi-threading version, but it's for a long shot. That's it.
Thank you. I think we can take one question. Sam, you can go ahead.
Hey, yeah, sorry, my camera fell over. Yeah, I guess this is more of a general question, but it kind of goes here as well for data structures. So one of the things I've been finding when I'm running simulations is that I have a quota for disk space, but also file number. So, you know, I'm fine for disk space, but then Ramses spams, you know, 1,000 files maybe per output. So is this something that you know, this new file format changes? And, you know, I guess also it's awesome if it's also merged into things like PIMSys and YT, where, you know, it's a lot easier to kind of arrange this stuff. Yes, actually, this is a different problem from the LightTimer, because the LightTimer is the format of the data, but with the integration of a parallel I/O, in this case, it's Hercule, but it could be the same for HDF5, for example. Then with parallel I/O, what's happened is all the data you want to output. So for example, it could be the LightTimer data of all the domains. They will be output in one file. For example, if you do collective I/O in HDF5, in the case of Hercule, they will be packed by a certain group of process, MPI process, to one single file, and potentially even multiple time steps in the same file. So it reduces significantly the number of files that produce Ramses. And this is how we actually achieve to improve the scalability of the Ramses I/O bottlenecks. Okay, yeah, that would be super cool. Thanks.
Okay, I suggest we take one last question before the break. So Jeremy, if you want to ask it.
Thank you for a very nice talk. I had two very quick questions. First one is how fast are the algorithms and how big is the gain? In the sense, do you think we can start is it in your plan to use this on the fly to make the communications faster, for example? Is this something we could think about?
You mean on the fly for the computation or
during
for
the simulation?
We discussed with some people at this year that are interested of using the compression to make, for example, a GPU version and to send a compressed stream of the data a little bit faster on the GPU, but it's not on the plan to integrate it to Ramses.
Okay. And second question was lossless compression is great, but maybe not fully required for the analysis. Have you looked into lossy compression as well? And
yes, that's a very good question. Actually, for the moment, we only look for lossless because that was the first requirement. But a lossy compression could be some advantage of not downcasting the data too simple, but have something with more precision than simple, but not a fully precision like double. So we will definitely look at lossy compression, yeah, to improve the compression ratio.
Thank you. Thank you to all speakers of this first session. So I guess we have the break now. We'll start again at 11:10. Yoki, I don't know if you want to say something.
Yeah, thank you, Clotilde. Thanks very much. Nothing really to add. I put a link again to the wonder.me. It's the same link as yesterday. I encourage you to go there and chat. And I also had the feeling that there were maybe more people that were interested in asking questions about the last talk and maybe others as well. Please use Slack. Address questions straight to Loic or the other speakers. And let's use Slack for continued discussions.